what I would do is I would try to interpret this, and I try to write it first in a way that I understand it better. So first of all, I'm not used to seeing negative 3x plus 3 pi over 4 on the inside. I would rather see the transformations with x isolated, kind of. So what I would rather do is factor out this negative 3 that we have on the inside. So I can't take it all the way out of the cosine, but I can do this. I could take the negative 3, right, and divide it out of these guys, both of them. So if I do that, this is going to become an x minus pi over 4. See? So by writing it like this, it's a little easier for me to understand what is going on. Okay, so let's talk about the 2 first, actually. The 2. So it's on the outside, it's being multiplied on, so this is a what? This is a vertical stretch. Being bigger than 1, being multiplied, being on the outside, that's a vertical stretch. So this is a V stretch. Okay, what it really wants us to do is to multiply all y values by 2. Okay, what does this negative mean out front? This is a reflect, right? Negative means reflect. So reflect over which axis? Yeah, over x-axis. So that would mean we're going to multiply the y's by negative 1. Good, okay, that's sort of getting going here. Okay, a little bit concerned about that negative 3 there. Let's talk about the 3 itself, first of all. So what does the 3 mean? This is multiplied on the inside, which is going to affect x. Horizontal. Right? So this is something horizontal. Is it a stretch or is it a compression? It's actually a compression. And you actually divide all x's by 3. Divide all x's by 3 is what it means, even though it says 3x, you know. You think that means multiply x by 3, but it doesn't mean that. Okay, and now that it's factored, it's pretty easy to see what this last thing means. X minus pi over 4 means what? Shift or translate, right? To the right, pi over 4. You can just think of that as 45 degrees. That's what it means. Okay, that leaves one unresolved issue, this little negative. But what kind of function did we say cosine was? Cosine is an even function. So do we need that negative? No. According to our rule for even functions, cosine of negative yada yada is the same as cosine of positive yada yada. Right? So I'm going to erase the negative. I don't want it. It's going to make me flip my graph backwards. It's just one more step that I really don't need on an even function. So I have full permission to just completely ignore that minus, because this is a cosine problem. Now notice I factored it out before ignoring it. That's important. I didn't ignore it at the outset of the problem. I factored it, then I tossed it. You know what I would have done with that negative if this had been a sine problem? I can't erase it, but I can pull it all the way out to the front. All the way out to the very front. Because sine of a negative is negative of the sine. See? So I would have pulled that minus all the way out, and it would have made that negative 2 in front a positive 2. Okay. So good riddance to that. That's one less transformation to think about. All right, so we got all of this in place. What we need now are some facts. Okay? So you need to kind of know what cosine looks like. If you don't know what cosine looks like, then you don't even have the fundamentals. So you can't even move it. How can you move a graph if you don't even know what it looks like? Right? Okay, so y equals cos x contains the points 0, 1, 90 degrees, 0, 180 degrees, negative 1, 270 degrees, 0, and 361. These are the the 5 points that I would have you memorize for cosine. I'll write them down again in a minute. What were my various dilations? Those are first, right? The dilations were, I was supposed to multiply by 2 for the y's and divide all x's by 3. So let's take care of that now. We said we were going to multiply y's by 2, divide x's by 3. Hopefully that's not too small for you to read. Okay, so what happens to these 5 points? Let's write them down in their new form. Okay, so they will now be the points. What? So I'm going to call on some people. Lester, what would the first point be if I multiplied y by 2 but divided x by 3? What would it look like then?
So, for
the first point.
okay, so y would be 2.
Yes?
And x would be 0.
Yeah, dividing 0 by 3 doesn't really do much, does it? Okay. All right, second point. Amna?
Y would be 0.
Yep.
And x would be 30.
Yep. Okay. Next one, Catherine?
The y would be -2, and the x would be 16.
Right. What's next, Fergus? Not here? Okay, I guess I should have taken roll. Let's go to Rebecca.
The next point is 90.
Yep. All right. And Daniel, last one.
Y would be 2.
X is?
And x
120. Okay. All right, next is reflections. We had 2 negatives in this problem, but we were able to resolve one of them by treating cosine as an even function. So we only have to multiply the y's by -1 here. Kind of makes you wonder why we didn't just multiply the y's by -2 on the previous step. I was trying to keep dilations and reflections separate. But if you want to next time, you can take care of the dilations and reflections during your dilations phase. So you could actually do dirt in the order of dr at the same time and then t. So the goal is to translate last. Do your shifting last. That's what really matters. Okay? Dirt is the best order. Okay, I'm going to multiply all the y's by -1. Okay, so it's going to be 0, -2, then 30, 0. That's not going anywhere. 60, +2 now. 90, 0, and 120, -2. There's my reflections. All right, and then the last thing I have to do is what? There's supposed to be a right shift by pi/4. Pi/4 is just another way of saying 45 degrees. So it's pi/4 to the right. That's my translate. But I'm just going to treat that as 45 degrees. Same thing. Okay. So let's go ahead and do that. Now, we knew it was a 45-degree shift to the right because when I factored out that -3, remember, this says x minus 45 degrees. So we know it's a right shift. When you're actually moving the points, if you want them really to go to the right, you need to add 45 to their x's. So don't double think it and subtract 45. If you're going to go to the right, you need to add 45 degrees to each of the coordinates to make them shift over to the right. Okay, so if I add 45 degrees, that's going to make this 45 degrees, comma -2. Right? 75 degrees, comma 0. 105 degrees, comma 2. 135 degrees, comma 0. And 165 degrees, comma 0. -2, I mean. Okay, so we got some points to plot. And what we'll do is we'll just put them on a piece of graph paper and connect the dots. There are many ways to do these problems. That is just how I chose to do it, okay, by treating the 5 points. Okay, so for graph paper, I just went online and I found this thing. This is from a website called Diet Calculus. Diet Calculus. Okay. .com. And I picked out of many, this is the one I chose because I liked the domain that they gave me. Okay, so what were my coordinates? They were 45, -2, and 75, 0. So 45, -2, 75, 0 would probably be right in there somewhere. And then I had 105, 2 and 135, 0. So 105, 2 and 135, 0. And 165, -2. Now when you draw these points, it really does look like a V, you know, upside down V, perfectly straight, and right back down again. So if you connected these using straight lines, they should look all collinear. So like the first three are collinear and the last three are collinear. Okay, but you obviously aren't supposed to connect them that way. You're supposed to make a curve. So you connect like this, actually. And we also understand that this is not the only period. This is just the one we were keeping track of. The graph actually continues on forever, right, in both directions. Okay, so you're supposed to do 4 of those last night. I just showed you my favorite technique. But you can also do this by just graphing y equals cos x, y equals 2 cos x, y equals -2 cos x, y equals -2 cos 3x, and y equals -2 cos 3x plus pi over 4, or minus. So I also want to do this example because I want to show you how to kill off that minus sign, how we got rid of that minus on the inside. That was cool. All right, we don't really have time for Q&A because our period is going to be over at 34. So what we need to do today is finish 5.4 because the scientists got a hold of this stuff and they gave it all sorts of interesting vocabulary. Okay? So what you and I would call sort of the height of this wave, right? From here to here, so like half the height. You and I would think, oh, that was just a vertical stretch. They would call that amplitude. And then what we would call horizontal shrinking and that sort of thing, they would call that change in frequency, change in period, change in wavelength. So they have their own terminology. When we shifted right or left, we call it shifting right or left. They would call it a phase shift, okay, and so forth. So if you had 2 waves and one of them was shifted, they would say one of them is out of phase, all right? And these are all important words to them, so we have to memorize them and learn them and use them, okay? But there's nothing new. It's old stuff with new terminology, okay? So you guys should pass forward your page 427. And so I don't forget, I'm going to show you the new page 427 assignment. It's right here. Oh, looks like it got deleted here. No, I actually don't want the note card today. I'm going to put up the assignment for tonight. Okay, so I think you should memorize these points on the sine wave. Scientists have names for those too. Crest, peak, nodes, all sorts of stuff there. Maybe you've heard some of those words in your bio class even. We're talking about sound waves and the human ear. We won't have names for those points, but you should know where they're at. 0, 0, 91, 180, 0, 270, -1, and 360, 0. Okay, memorize these 5. If you know 5 points, you're good to go. Notice that 3 of them are x-intercepts, and we have 1 maximum and 1 minimum. Okay, you also want to know the range is -1 to 1, and you want to know that sine is odd. It's an odd function. So I told you yesterday, if you're going to draw more periods, you have to be careful how you draw this left-hand piece. you need to draw this coming down. I've seen students draw the left side where it looks symmetric to the y-axis. So I've seen people draw the left side like this. They'll take the left side and go up like that. That can't be right because that's not odd symmetry. Right? That's not the kind of symmetry an odd graph would have. Okay, so you want to draw it going down. And then over on the right, it goes on. Before we look at the cosine graph, I need to point something out to you. It's a calculus idea, but it matters now too a little bit. Whenever you're drawing a curve like this, you can't make it too steep because some people draw their waves like this, semicircle, 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 semicircle. See the top of the board there? That's not really what this is. This is not a bunch of semicircles glued together. Okay? That might be some other kind of wave. But listen, this is not that steep, really. In fact, if you look at this as a roller coaster, these little lines indicate your direction of travel as you move along from left to right. Does anyone know what these little guys are called? Okay, these are called tangent lines. Okay? You're like, oh, I understand. Tangent lines in geometry, we draw them so that they touch the curve once, right? I just drew a bunch of green tangent lines. The steepest tangent line on the whole picture occurs at 0 and at 360. I'll make them longer. There's one right there and one right there. That one's off a little bit. Let me move it. Okay. Those two tangent lines have slope 1. Okay? Slope 1 is not very steep. 45 degrees with the x-axis. So this angle right here is 45 degrees. So don't make it too steep. If you draw a bunch of semicircles, it's not going to look right. Okay? All right, let's go to the next graph. This is the cosine graph. We're going to memorize 5 points. This time, there are 2 relative maxima, 1 point at the bottom, and 2 x-intercepts. And the points are 0, 1, 90, 0, 180, negative 1, 270, 0, and 361. I'm labeling them in degrees. Obviously, my graph is shown in radians. Same thing. Okay? Memorize those points, and you should be good. Anyone can connect the 5 dots after that, right? Range is still negative 1 to 1. As you know, if you wish to draw more periods, that's easy. No one ever gets this wrong. I just drew in purple a little bit more graph for you. Again, what was the steepest any tangent line ever gets to? Slope 1. There's a slope 1 line right here. Don't make it any steeper than that. Okay? All right. Both of those graphs are called sinusoids. Sinusoids. So some people might say, well, hold on, that second graph should be called a cosinusoid. No, they're both called sinusoids. So if someone says that an object is showing sinusoidal behavior, they're not saying it's a sine wave behavior. They're saying it's a sine or cosine wave. You can't tell from the word sinusoid if it's talking about sines or cosines. So that's a really weird word, but both sines and cosines are referred to as sinusoids. Okay? I always thought it sounded like a cold medicine. It's like some sinus Altoid or something that just came out. All right, let's go on. Okay, transformations. We did transformations. We're done with transformations. We did it for the warm-up. But, like I said, there's a lot of vocabulary when it comes to transforming sinusoids. First of all, we have this right here. You and I would call that the number that gives a vertical stretch. Or maybe if it's negative, the number that causes an x-axis reflection, right? But a scientist would look at that number and they would take its absolute value and call it the amplitude. So what you and I call a vertical stretch, they call an amplitude. See? This number here, by the way, this is the Greek letter omega, if you don't recognize it. This number is responsible for changing the width of the graph, right? It is responsible for dilating horizontally, like we saw in the warm-up. So the scientist interprets it this way. The scientist wouldn't say, oh, look, your wave got compressed, right? Let's say the wave was like this. And now it's the one in green, so it's been compressed. They don't say, oh, it's been compressed. They would say, oh, the period was shrunk. Or they would say, oh, the wavelength is smaller. Or they'd say, oh, it's more frequent now, higher frequency. So these are words you hear in music too, right? If a wave is higher frequency, it means more vibrations per second. One way of saying that is fewer distance, smaller distance between wave peaks. There's so much vocabulary. But understand that they would interpret this as if a graph started at 0 and 360, the black one, but for the green one, if the graph can do a full cycle in just 240, from 0 to 240, they would say, oh, the period changed. See? Or the amplitude, or the wavelength changed, or something like that. So they have their own terminology. And they would say that the period is going to be 360 divided by whatever number was in front of the x, or 2 pi over omega. Okay, so 2 pi over omega is sort of how you calculate your period, is what it's called, period. We'll do an example in a minute. It's a little bit confusing because of the terminology. Okay, now, remember in the warm-up, I had you guys do a right shift. It looked kind of like a left shift, but it's because there's a negative here. Once I factored it out, you can tell it was a right shift by 45 degrees. Remember that? Okay. So effectively what we did was we divided that 135 by -3. That's what we did. So if you divide this number here by the omega, that will tell you what your shifting is, your horizontal shifting. Scientists call it phase shift. Whatever. I call it horizontal shift. By the way, this is the Greek letter. Does anyone know? Phi. Phi. I call it phi. Some people call it phi. I don't care if you call it phi, phi, pho, or phum. Doesn't matter to me. Okay? Probably the only thing that we would agree on with the scientists here is this last number. I would call it a vertical shift. The scientists would probably call it a vertical shift also, although they might call it an equilibrium point or something like that. So we have different vocabulary, but we're talking about the same thing. This happens a lot with math and physics. It's very unfortunate, but scientists and mathematicians go back and forth about what to call things. Okay, this happens all the time. Okay, but that's the way it is. The range of the function. Now remember, if you're going to move a graph, right, from here, so looking down here on the bottom right, if you move a graph from here down to here, you're going to change the range, right? What once was wiggling between -1 and 1 is no longer wiggling between -1 and 1. Maybe now it's wiggling down here between -5 and -7 or something, you see. So by moving the object, we can easily change its range. So we need a formula for that. Here is your formula for range. It's b minus the amplitude, comma, b plus the amplitude. All right, let's try a couple examples in our last 10 minutes. We're going to answer all 4 questions for these 4 problems. Okay? All right, so the first one asks, what is the amplitude period, what is amplitude period phase shift of the given sinusoid? I think we should factor out the 2. Okay? So let's do that. So we're going to write this as y equals 3 times sine of 2 times x minus 2 plus 2. Also, the formulas you saw on the previous page were designed for radians. So do you see any degrees symbols in this problem? Any degrees symbols?
Yeah.
Really?
No.
Where was the 100?
That's part B. In part A, I don't see any degree symbols. So we should be good using the formulas that the scientists gave us. Okay, so, and it's not all scientists, but partly responsible, some math people here too. So let's take a look at the formulas, and we'll just run through this. So your A is just chilling right in front there, and you're supposed to do the absolute value. Okay, so the amplitude is simply going to be the absolute value of 3, done. Okay, the period is going to be 2 pi over omega. Omega is chilling right there. I circled it in red. It's 2 pi over 2. So what is my period? What's 2 pi divided by 2? Pi. Okay, my phase shift, I'll just abbreviate it PS. The phase shift, you can use the formula if you want, but I don't need it. I'm looking at a factored problem right now, and I can tell you without anyone's help that this thing is shifted to the right 2. See that? So the answer is 2. If it had been a left shift, I would have gone negative 2. Okay, so I don't use a formula for phase shift very often. And then for range, that's using this last number here that I just circled in green. You're supposed to do that number plus the amplitude and that number minus the amplitude to figure out the extreme y values for the graph. So if the amplitude was 3, remember back in the very beginning, it would be 2 plus 3 and 2 minus 3 are your extremes. So basically 2 minus 3 comma 2 plus 3 is the answer. So the range is -1, except I wrote 2 plus 5. It's -1 comma 5. Okay, so it's 2 minus 3, 2 plus 3. Let me rewrite that a little bit. Okay, that's how you do it. So why am I giving you 4 examples? It's because sometimes we have to wrestle with that odd-even function thing. All right? So let's take a look at this next one. Also, this next one has degrees in it. That's confusing. Okay, so let's take a look at this one. Part B has degrees. Why don't we just change it to radians now? That way we don't have to worry about it in the future. So I'm going to take this 100 degrees, multiply by pi over 180. So that's going to be 5 pi over 9. There we go. Now it's time to factor out that 3, like we did on the previous problem. Pulling out the 3, we get x minus 5 pi over 27. All right, let's run through our 4 calculations. Okay, so amplitude. Now there's a -5 out front, but what's the actual amplitude?
5.
It's supposed to be the absolute value of that number in front, right? So this means you never give me a negative amplitude. If I ask you what's the amplitude, never say -5. It's supposed to be the absolute value of what's in front. Okay. Let's talk about the period. The period is supposed to be 2 pi over whatever omega is. In this problem, I'll circle it in green, it's right here, 3. So the answer is 2 pi over 3. The phase shift, I've got mine already factored. I already know the answer, 5 pi over 27. Done. Range, for range it's going to be this number at the end, right? Plus or minus the amplitude. So it's basically -1 minus 5, -1 plus 5. That's your range. So basically -6 is the extremely small value for y, and +4. So -6 to +4 is your range. Okay? Now this next one has a negative on the inside, so that could present a problem because the formulas that I gave you only work if omega is a positive number right here. Okay? You may not use any of these formulas, well, you can use virtual, but you can't use the period or phase shift rules unless your omega is positive. That's very important. So what I'm going to do is I'm going to get rid of that negative right now. So remember on the cosine example, what I did with this negative is I actually just erased it. Remember that? I can't do that here. This is not a cosine problem. Cosine was an even function, so that negative made no difference. I just factored out and then I destroyed it. But here on the sine problem, that negative is important, but it can be placed somewhere else. So here's what I'm going to do. First I'm going to write it as y equals 0.2 sine of, and I'm going to factor out that negative half. And I still don't really like that negative on that half. And I can't erase it, but I can move it. I'm going to move it to the outside of the very outside. So literally bring it all the way out to the very, very front of the whole problem. Now I don't have that negative on the inside. And my formulas will work from the previous page. Okay, that's what you can do with an odd function. Just pop it all the way out to the front. Okay, let's run through the 4 questions. Amplitude is, can you tell by looking? Class response? 0.2. Thank you. Not negative 0.2, right? Period is 2 pi divided by, what's my omega? 1/2. Okay, so 2 pi over a half. What's 2 pi over a half? 4 pi. Okay, what's my phase shift? Since I have it nicely factored, my phase shift is just chilling right here. 2 pi to the right means phase shift 2 pi. Okay. And lastly, my range. Range is, and this is kind of silly, I put a 10 here. Forgot to write it. It's that 10 at the end plus or minus the amplitude. Okay? So it's going to be basically 10 minus 0.2, 10 plus 0.2. In other words, 9.8, comma 10.2. For my range. I might have time for this last one. I'm going to factor out that negative pi to make this inside look a little bit simpler. If you don't like that negative on the pi, what am I going to do with it? I can't pull it out. This is an even function now. I get to ignore it. Right? With an even function, I can just scratch it. So that was a negative there under that scribbly purple thing. Okay, so my answers are, what's my amplitude? This is actually a pretty easy one. Amplitude is, what's the number in the front? 1, yeah. Amplitude's 1. Period is, this is an interesting one, 2 pi over, your omega is pi this time. So 2 pi over pi, what's my period? 2, interesting. What's my phase shift? That's easy. 2. It's right here. It's already nicely factored. And the range is, yeah, it's basically 100 plus or minus the amplitude. The amplitude was 1, so it would be 99 to 101.